Hi, in this video, I'll show an example of why an improper integral of the discontinuity type is dangerous and tricky for calculus students. And then I'll show a step-by-step approach on how to handle these kinds of integrals. All right, let's take a look at this integral from -1 to 2 of 1 over x squared dx. The unsuspecting student would look at this and rewrite it as integral from -1 to 2 of x to -2 dx like this. And you tell yourself, you know how to integrate this, right? It's just integral of x to the n is equal to x to the n plus 1 over n plus 1 plus c. That's the indefinite integral. So you're going to integrate this into x to -2 plus 1 over -2 plus 1 like this from -1 to 2. Which is x to -1 over -1. And let's rewrite this in a form that we can easily plug in. The whole thing is just -1 over x from -1 to 2. Now you plug in, you get -1/2 minus -1 over -1, which is -1/2 minus 1 equals -3/2. And you would think that that's the answer. That's the end of it. But that's wrong. It's incorrect. This integral is not equal to -3/2. Let me show you how I know that. The integral we're looking for is from -1 to 2 of 1 over x squared. And this is the graph of y equals 1 over x squared. It passes through this point here, -1 comma 1, and that point there, 1 comma 1. And the integral from -1 to 2 of this would be the area under the curve from -1 to 2, so it's that entire area. Well, that cannot be -3/2. First of all, because that area is completely above the x-axis, so the area under the curve will be a positive number. It cannot be a negative number. So, wrong sign. And second of all, it's also the wrong value. Because this area right here, this little square, by itself is already equal to 1. It's just 1 by 1 square. And for that matter, there's another 1 by 1 square over here. So that's also equals to 1. So together, the two of them are already equal to 2. So there's no way it can be -3/2. So wrong sign and wrong value. Okay? The negative sign is wrong and the 3/2 is wrong. Then the question is, how come? Where did the wrong answer come from? And it comes from this. That vertical asymptote there. The function y equals 1 over x squared is undefined at x equals 0. There's a discontinuity at x equals 0. The function does something funny at that point, and when you do the antiderivative at this point minus the antiderivative at that point, you fail to recognize or take into account anything that happens in between. And that is why you got the wrong answer. So now let's do it right. All right, the situation is that we have an interval from -1 to 2, and there's a number 0 here where there's a discontinuity, where the function is not continuous at x equals 0. And the idea is we're going to avoid going from -1 to 2, rolling over that point of discontinuity in between. We're not going to do that. We don't want to do that. We want to have an interval that does not roll over that 0. That means we want an interval that stops at 0 and then restarts again from there. We want to go from -1 to 0. Okay, -1 to 0. There's a discontinuity here. Let's not go over it. Let's start again at 0 and go to 2. If we separate it into those two intervals, then there will be no discontinuity in the inside of any interval. In other words, I'm going to do from -1 to 0, and then from 0 to 2 separately. So now I have the integral of 1 over x squared is negative 1 over x. We just did that. And this one will be from negative 1 to 0. Plus the other integral is also negative 1 over x, and it's going to be from 0 to 2. And now we're going to plug in. We're going to plug in negative 1 over 0 minus negative 1 over negative 1. Well, this doesn't work because, there's no such thing as 1 over 0. So we're going to do it as a limit. We're going to be the limit of negative 1 over x as x goes to 0. Except that this is the interval from negative 1 to 0 like that, right? So if you're approaching 0, you're going to be approaching it from this side. You're going to be approaching 0 from the left. And therefore, it's really the limit as x goes to 0 minus. And all of this is the first integral. Now the second integral, we plug in the 2, negative 1/2 minus. And again, it would have been minus 1 over 0, and we don't want to do that. So we're going to do a limit of negative 1 over x as x approaches 0. This one, though, is from 0 to 2 like this. So if you're approaching 0, you're approaching 0 from that side, from the right. So this is a limit as x approaches 0 plus. Now, the 1 over x by itself, because x approaches 0 from the left side, is a negative number. So 1 over x approaches negative infinity. And then minus 1 over x approaches positive infinity. So this whole thing is a positive infinity. And this one is minus 1 plus negative 1/2. Now, when x approaches 0 from the positives from the right side, then 1 over x approaches positive infinity, and then minus 1 over x approaches negative infinity, and then have a minus in front. So it's minus a negative infinity like that. Now you see the importance of knowing which side you're approaching the number from, because it affects which infinity we're dealing with. Now we simplify. Infinity minus 1 minus 1/2 minus is a plus infinity. Well, infinity plus infinity is infinity. So this whole thing is equal to infinity. And the word we use is that the integral diverges. This integral is equal to infinity. The area under the curve, 1 over x squared from negative 1 to 2 is infinite. You can see that if you look back at this graph, the shaded area is pretty wide. So as it goes up, it keeps adding large numbers all the time, and that's why it gets to infinity. If you sort of compare it with this branch of the graph where the thickness is pretty narrow, and you sort of suspect that maybe it keeps on adding, of course, but maybe at some point it'll cap out and it won't go to infinity. And you would be right. But that's the story for a different time. So this kind of integral is what we call an improper integral of the discontinuous integrand type. That's one type of improper integrals. The other type of improper integrals is an integral with infinity at one or both limits. So it could be from negative infinity to some number. It could be from some number to positive infinity, or it could be over the entire number line from negative infinity to infinity. Those are improper integrals, and they're easier to recognize because you see the infinity in the limits. There's no missing it. Whereas this type of integrals, if you're not paying attention, you'll miss it. You'll think that it's just another integral, right? So to do these kinds of improper integrals, the very first thing you need to do is to recognize them. So for example, you're given an integral from a to b of fx dx. Then the first thing you want to recognize is that the fx function is the type that can give you trouble, that can be discontinuous in the segment a to b. Luckily for you, in the typical calculus class, this type of improper integrals come in only a few things. So if you can remember them, is that if it has some sort of denominator, then it will be discontinuous at the points where the denominator is equal to 0. Right? You remember all that from finding domain of a function in algebra. Also be careful, denominator could be disguised as a negative power. A denominator could also be disguised inside some trig functions. Tangent is sine divided by cosine, so there's a denominator there. Cotangent is cosine divided by sine. Secant is 1 over cosine. Cosecant is 1 over sine. All of them have some sort of denominator that at first sight you may not see it. And finally, there's another function that could be discontinuous, not because it has a denominator, but because it has a vertical asymptote, and that is a logarithm function. Once you recognize that fx is of a type of function that could have a discontinuity, then you find it. Or rather, find them. There may be many points of discontinuity in the interval that you're integrating over. So for example, you have an interval from a to b, and you could find a point of discontinuity at maybe some x1 here, maybe some x2 here, and maybe even at one of the endpoints. So let's pretend that you even found it at endpoint B. Then number 2 is to break into intervals. Break into many integrals for each of those sub-intervals. So for the same example, I'd break from a to x1, x1 to x2, and x2 to b. So let's just say that the antiderivative of little f is some big F. Then I start plugging in, but now I have to watch out for the limits at points of discontinuity, and also I watch for the one-sided limit, okay, which side it's on. So I need to watch the one-sided limits at the points of discontinuity. So for example, the first integral would be f. It would have been f of x1 minus f of a. Okay, it would have been that. Except that it's not, because f of x1 is not continuous. So I have to make it limit of f of x as x approaches x1. Well, which side of x1? Well, here's a, here's x1. Then that means I'm approaching it from this side. So it will be like that. So that's the first integral. The second integral, we're looking at the interval from x1 to x2. Well, within this interval, I'm approaching the x1 from the right and approaching the x2 from the left. So it's gonna be limit as x approaches x2 from the left minus the limit as x approaches x1 from the right. That will take care of the second interval. And then the third interval, or integral from x2 to b. And remember that we're, in our example, we found points of discontinuity at both. So I'm going to have to do it again here. right? So that's the kind of thing I need to pay attention to. I need to watch the one-sided limits. So finally, I get to evaluate all the limits. I evaluate the whole expression. If the value is either positive infinity or negative infinity or does not exist, because sometimes these limits, they may not go to positive infinity or negative infinity. They just sort of oscillate, let's say, between -1 and 1. So it won't arrive at any limit, won't approach any single number. Then we say that the integral diverges. All right, so that's the idea. Here's a summary. Hope this helps. Any questions or comments, put it in the comment section below. Like, share, and subscribe for more contents. And thanks for watching. Bye.